Yeah, so it's you know our buddies where is it? This is what it's supposed to look like, and see, this is the nice. It's supposed to go like this, okay? And I don't know why my thing is acting all funny, but I'll try this again. I'm gonna this time express our gradient descent algorithm in matrix notation, okay? Let me put my notes. Okay, so in matrix notation, we have to define a few things, okay? So we're still talking about linear regression. Okay, and so we're going to have, so I'm following, maybe I'll post a link to this, this set of notes here, okay? So, you know, we fit a model, right? Which is basically, you know, y hat is equal to, you know, a linear model, okay? So we're going to call our y hat our hypothesis function. Okay. And this is going to be, so our intercept is going to be theta 0, and then our slope will be theta 1, x1, okay? And what we can do is we can, essentially, we can express our, you know, we've got x and y, and we might say this is 1, 2, 3, 4, and 2, 6, 4, 8. But what we can do is we can turn x into you know, a 4 by 2 matrix where the first column is all ones and the second column are the values that we want. Okay, and so in this case, h of x essentially becomes, so if this is if we call this x0 and this x1, then we've got theta 0 x0 plus theta 1 x1, okay? And if theta is a matrix theta 0, theta 1, then h of x can simply be explained as theta transpose, wait. I'm sorry. It'll just be a x theta, right? Not dot. Okay. So this is, you know, our line of fit is this. Okay, and then and we'll define our cost function, okay, which we try to minimize. Okay, so this is for ordinary least squares. It's the you know, sum of squares residuals, right? Okay, and so you know I'm using Andrew Ng's notation. So this, so he defines the cost function j. Okay, j of the parameters that we're trying to optimize, theta. Okay, and he defines this as the function with our current values of theta of our x values minus our y values, okay, and over all of our data points, okay, and we're going to square that difference and sum them up, okay, and to help deal with the when we take the derivative, the 2, he just multiplies it by a constant of 1/2, okay? So this, when we multiply by the derivative, or when we use the power rule, is this, okay? So this is essentially ordinary least squares. You know, I think we're accustomed to seeing the actual value minus the predicted value, but in this case we're doing predicted minus the actual. But you know, when we square it, it's not really going to make a difference. Okay. All right, and then our gradient descent algorithm is you know, the next value of theta of our parameters are going to be the current values minus our learning rate alpha times the gradient of our cost function. Okay, so we're going to just take the gradient of this thing, you get times, what is this, chain rule, So what does this become? This becomes and I think the derivative of, okay, so if we look at what what is the derivative of this thing, okay? So h of theta is really just x times theta, right? Or theta, x times theta minus y. So the derivative of this thing just becomes x. Okay. Here, let me just circle this part. Okay, and then so we've got the summation of all of this. All right, and so what we're going to do is we're going to just subtract, apply this into our algorithm. So we, with each update, theta becomes the theta plus or not theta, yeah. Sorry. Theta minus alpha times the summation of where x times theta. Okay, so let's try coding this, and I hope this works this time. Someone's yelling out there. What's going on? Okay, so I'm gonna set our, this will just be repeat 1 4 times. Excuse me. Okay, so this will create our X matrix. You know what, I should clear my environment. Okay, so that's our X. Y will do as.matrix. Okay, and we can print out Y, and there we go. Okay, and okay, and so we can we will define theta to be a matrix 0 0, and then you know, our fitted values h will be a function of x and theta, okay? And basically we're just going to do x times theta. All right, so let's just see h of x and theta, and that seems good, and I can try modifying that, and that seems to be working. Our fitted values, okay. And so our gradient we'll define as a function of x, y, and theta. And so what do we have? We have x times theta, that's our fitted values, right? Minus our values y. Okay. Wait, let me go back and just check. So it's x times theta. So this is x times theta minus our values y. You know, multiplied by our values x, summed up over alpha. Okay. So to get this to work, so this is currently 4 by 1, and effectively I need to get it into a 4 by 1, so I have to multiply this by, I want it to be 2 by 1, so that's I'm gonna take the transpose of x and multiply by that. Okay. And this should sum this up. We'll try this. Okay. So I got gradient of x, y, and theta. Okay. That seems correct, right? So we've got, all right, let me just think about this. So x is that, theta is currently that, y is that. So the gradient, so if this was 0, 0, gradient of x, y, and theta. Okay, so this is the direction that that we're supposed to move. Okay, so that's so we can see that's kind of a big amount. Now I'm fearing I'm going to get the exact same results as I did last time, but let me just see. Okay, so we have to set our learning rate. So so we could see the direction that our gradient returns is quite big. So I'm going to say our alpha is going to be a very small value. Okay. And what we're going to do is we're going to run this. Let's do 10 iterations. No, we'll do 100, and we'll just see if this works. Okay. So I guess before we run it, let's just kind of see where we're headed for. Okay. So I mean, there's a few ways we can do this. We can, you know, the fit values are what? X transpose X inverse, or I guess, you know, transpose X inverse X transpose Y, right? Transpose X. Where am I going? Transpose X, Y. So we can see. So our fitted. Where am I? Okay. So we can just see. Solve. This is not how you would ever actually solve linear equations, but computationally. So that's X transpose X quantity inverse, and we want to multiply this by x transpose y. What? Oh. I'm using capital letters. Okay, so it says our intercept is 1.0 and our slope is 1.6. Okay, and we can also verify this by saying, explain y as a function of x plus 0. Okay, and then and it says, the coefficients are 1.0 and 1.6. Right? Is this okay? So this is what we're hoping our optimum function goes. So intercept should be 0, or not 0. Intercept should be 1, and slope should be 1.6. Okay, so what are we going to do? We're going to take our theta matrix, theta matrix, and update it with theta minus alpha times the gradient of x, y, and theta. Okay, so we'll start off with theta as 0, 0, and then let's hope this works. I guess before I run it, I just want to make sure everyone's okay with this implementation of the gradient descent algorithm in kind of matrix form. Questions? Yes.
Why do we have to set the theta as a matrix?
Why do we have to? Oh, those are just our initial estimates of theta.
So it starts from 0 to
That's just, I arbitrarily chose that. Okay. So let's just run it and let's see what our results are. That's not so great. Let's run it a little bit longer and see what happens. Okay, that's pretty good. That's pretty close to 1 and 1.6. Okay, let's okay, let's try this again, and then I'm gonna create this is the most inefficient way to do it, but I'm gonna do theta history is gonna be a matrix of let's see, NAs with n row, we'll do 1,000, and number of columns will be 2. And what we're going to do is we're going to say theta history is going to, in row I, we will take, we will insert theta. I think this will work. Okay, so we're going to start off initial values here. Theta looks like that. Let's check out the head of theta history. So starts off, okay, from 0, 0, it moves up to there, and then tail theta history. Okay, yeah, right around that. So let's see if we can plot these. X sub 0 and x sub 1. Okay. So I'm going to plot my gradient, my contour lines, and I guess I can shoot. Okay. So something, I don't know what I did wrong with this function. Come on. Okay. So we'll okay, let me add points from theta history and Okay, so what I'm hoping is we see something start off around, well, the first line's not 0, 0, it's the next one, and I'm hoping it traces out a path that goes into the center. I haven't run this, so. Yeah, that's not quite what I was looking for, huh? It's behaving the same way as my other stupid algorithm, huh? Okay. Yeah, okay. Now my brain hurts because, well, so it's working, but it's also it's not behaving the way I'm expecting, and I haven't. I'm not sure why. This is annoying. Okay. The other algorithm does the same thing, where it kind of it walks up, and then it like makes a turn. This one that I did over here, I was just playing around with different values of alpha. So let me just see if it'll do the exact same. -2, 1, and okay, so I'm gonna just try 0.02. Let's just try another one. -2 and 1. That's stupid. Product 2 doesn't match the length. What have I done? That's correct. That's correct. Okay. Okay, that's also correct. All right, let's plot our points. Theta history type equal del. Yeah, again. All right. To me, this is strange because maybe this is how. Okay. Oh, I thought the matrix implementation would fix it, but upon closer detail, it does not. Okay. Well, I'll post my code up, and yes.
Why do you think that there is a problem here with the implementation?
You know, well, it's working. It does take me to the optimum, which is a good thing. I was expecting it, and I feel like I'm just multiplying something wrong. I feel like I'm missing a constant. Like I need to adjust the vector that it travels a little bit this way, and it'll work correctly. Because what the gradient descent algorithm is supposed to do is it's supposed to travel along the slope of steepest descent. Okay.
Yeah, but in that case, I think you have to set alpha to a specified value to get a 3D descent.
Well, no, it's supposed to travel tangent to these contour lines, and so so the fact that it's taking sharp turns is a little odd to me, and so I'll share my code. You can take a look at it. Perhaps I have made a silly mistake, and I'll keep reading here about what's going on. I mean, the good news is that it does converge to the correct values, but the bad news is it's not doing it in the way I was expecting. So, well, I guess we'll end there for today. I'm sorry, it's a little strange here, but and I'll share my code for both implementations, and you can try playing around with them.